Welcome, everyone. Welcome to iTelescope and to another really wonderful webinar. I'm really happy to introduce to you today. By the way, my name is Christian Sasse. I'm the astronomer in charge for iTelescope. I really love this job because the webinars give us so much information. Today we have Abbe Whitford, who is a PhD student very early, as John already remarked, from the University of Queensland in Australia, 4 a.m. there. So Abbe Whitford has a very interesting topic because she's going to explore the connection between large-scale structures of the universe and going right down to the evasive neutrinos of cosmology and particle physics. So that's really on the cutting edge of everything in physics and science. Abbe, welcome, and thank you so much for getting up so early and making this so interesting for you. How are you?
I'm good, thank you. Very good. It's so cool to see people from so many different places.
Yes, so it's all yours. Just tell me when you want to share the poll questions, and it's all over to you.
Awesome. Okay, I'll just share my screen. Okay, does that look good to everyone?
Yes.
Awesome.
Yes.
Okay. So thank you for coming. So today I'm going to talk about something called the large-scale structure of the universe. And this is what I've been working on for my PhD and also my research in my honors degree, and looking at using this to test models of cosmology and even contribute somewhat to understanding or helping to understand particle physics, mainly through, as Christian said, through understanding neutrinos, which I'll explain what they are when we get up to that part. Okay, so just to start off, this slide here, so you can see this plot. So along the bottom of the plot, we're looking at increasing distance, and each single point on this plot, it actually represents a single galaxy. So this figure was made by the DESI collaboration. So DESI is the Dark Energy Spectroscopic Instrument Collaboration, which is a collaboration of hundreds of scientists who are looking to understand, using the large-scale structure of the universe by mapping out the universe with up to what, right now in this plot, the data shows about 10 million galaxies, but they will collect data for up to 35 million galaxies over their entire survey. And they're looking at using this large-scale structure to improve our understanding of cosmology, particularly through their goal, which you might be able to guess from the name, is through understanding dark energy. That isn't what I'll talk about so much today, but I'll talk about using this large-scale structure, which you can see in this kind of CT scan. So this plot is moving, and it's because they're scanning through different points in the sky. And using this structure, you can see in this plot these filaments and these bits where more of the galaxies are clustered together, and other parts where there's like gaps or what we call voids. In understanding this structure and how it's formed like this, and what this tells us about what different things kind of make up the universe, the amount of matter and radiation and even dark energy. Okay, so just to get started, to give you some context, so most people, when you talk about space, they just think about the solar system, so our planet and all the other planets in our solar system revolving around the sun. But our galaxy, the Milky Way, is made up of billions of stars. And if you zoom out, or imagine kind of zooming out even further, there are clusters and clusters of galaxies. And when you go out kind of even bigger again, so this last plot here is also a plot made by the DESI collaboration, actually made by a student member, Claire Lamar, another PhD student. This shows the data collected from their year one survey. And you can see the structure here from where every little point here is an individual galaxy again. So you can see these big filaments, or what we like to call the cosmic web. And the gaps in the data show what we call voids. So to give you some context for what these scales are, so a single galaxy, like the Milky Way, has a scales of, or lengths of the diameter of about tens of kiloparsecs. So what's a kiloparsec? Well, one parsec is about 30.9 trillion kilometers, or in light years, which is very popular to use, about 3.26 light years. So if you could move at the speed of light, it would take you about that long, 3.26 years, to travel one parsec. Clusters of galaxies are tens of megaparsecs. So I should say a kiloparsec is 1,000 parsecs. So galaxies have sizes of about thousands of parsecs. Clusters of galaxies are tens of megaparsecs. So that's millions of parsecs. And when you look at this plot here, we're looking at like giga-parsec scales. So a gigaparsec is thousands of parsecs, for context. So this is the kind of length scale and scale of the structures we're talking about when I say large scale structure. So, I mean, why do we care about the large scale structure of the universe? So it looks amazing, right? We can map out the universe by looking at these individual galaxies and seeing this huge structure. But the reason why it's so important for cosmology is that the large scale structure today is a consequence of, I guess, what the universe is fundamentally made of, that being the amount of matter, what we call normal matter, and what we call dark matter, that I'll talk about later, as well as how much radiation was present in the early universe. So radiation being photons, which are particles of light, or any other kind of particle like neutrinos, which I'll get to later, which are very light particles and behaved kind of like a sort of radiation in the early universe, as well as the amount of dark matter that exists. And also, the large-scale structure is dependent on our expansion history. So what this plot is meant to be showing here is kind of like, probably not exactly to scale, but roughly an idea of how the expansion of the universe has changed over time. So we believe there was this big bang, which on the most left part of the plot, and then there was this rapid period at the very early universe. So moving from left to right, where you have this big sort of expansion. So that is called inflation. And then as time continued to go on, the universe kept expanding and it kept getting colder. And because it cooled, the gas and the dark matter could kind of collapse gravitationally. And over time, this formed the very first stars, and this formed the very first galaxies. And then we believe 13.8 billion years later, we have the present day. And all of this large scale structure, you can see how it formed and the different length scales or distance scales you can think of where we have this clustering of galaxies depends on how strong gravity is, how much matter there is, and how quickly the universe expanded at different times. So this plot here is meant to be kind of, what I'm meant to be highlighting here is these kind of key events that happened in the universe's expansion history. So what this plot is showing on the y-axis going up and down is kind of like the relative amount of radiation is the green dash line, the relative amount of matter, and the relative amount of dark energy at different points in time. So going from left to right, you're going from what would be the Big Bang, sort of at the beginning, and later on at the end, the present day. So in the very early universe, you had this period we call the radiation domination epoch. So what this means is that basically most of the energy in the universe, or the energy density in the universe, was radiation. At some later point in time, the radiation density decreased, and you can see where this blue line starts crossing over. This is where the density of matter increased, and from this point onwards was higher than the density of radiation. So you have this matter domination epoch, and then a very important event in cosmology called recombination. This was the point in the universe, which is something very roughly 4,000 years after the Big Bang, where the density, the universe had expanded enough that protons and electrons could combine together to make hydrogen in the universe. And hydrogen and helium is what forms most of the normal matter we see in the universe today. And then we believe, from our understanding, that the universe is currently accelerating in its expansion due to something we don't really understand, but we call dark energy. A couple of billion years ago, the density of matter started to drop off, and the density of dark energy started to be the dominant component of energy density in the universe, and it is driving the accelerated expansion today. But if there's anything you take out of these first few slides, it's that the amount of different stuff that we have in the universe is what determines how the large-scale structure looks today, how much matter clusters, how big or small voids are, how big these filaments are, whether you have lots of little tiny ones or only lots of big ones. And we'll come back to this later. But that's the main thing that I wanted to sort of get across here, and why, of course, we care about large-scale structure. So now I'm going to talk, I've kind of split up the rest of my talk into two parts. So firstly, on what I focused on for most of my research up until about maybe a bit less than a year ago, which was using the motions of galaxies to probe this large-scale structure and to test our models of cosmology. By models of cosmology, our models mean kind of how our fundamental principles of cosmology, such as how isotropic or how the universe we think looks in different patches. So we assume in cosmology, the universe is kind of like roughly looks the same everywhere on average, so very approximately, and that it looks the same no matter what direction you look in. So this is part of our like model of cosmology. And on top of that is our model accounts for how much we think there is of the amount of matter, the amount of radiation, the amount of dark energy. So when we say testing models of cosmology, we're testing these ideas, and we're even testing our understanding of gravity, because we assume that the models that we've tested for gravity that work on Earth or in our solar system, just from looking at the orbits of planets, are the best models. But obviously, when you go to an even larger scale, the large scale structure of the universe kind of scale, you can test that even more, because how quickly galaxies formed and collapsed depends on how strong gravity is. So this allows us to test our understanding of this. So why do galaxies have motion? So what are these motions of galaxies that I'm talking about? So there are kind of two things that you can think of that make galaxies move, two very basic things. So firstly, I mentioned before that the universe has been expanding since the Big Bang and is still expanding today. So all galaxies have a component of motion, which in cosmology, we like to call the Hubble flow or their recession velocity, but you can just think of it as their motion due to expanding space. So all galaxies, you could imagine like this grid marking the locations of galaxies in space, and this grid is expanding. That expanding grid makes all galaxies move away from each other constantly. So this is their motion due to that. And the way we can measure this motion, well, firstly, actually, I guess I wanted to say this motion was discovered in about 1929 by a very famous person called Edwin Hubble. So hence why these motions of galaxies are called the Hubble flow. So he was the first person to discover that if you plotted the distances to galaxies, so he measured the distances to a few galaxies and measured their velocity on one axis, and you get like this increasing velocity with distance. So that was the first evidence of the expanding universe. And for a long time, this law where you show that there's this relationship between velocity and distance has been called the Hubble law. However, it now gets called the Hubble-Lemaitre law because another physicist, who I believe is also a priest, Georges Lemaitre, also predicted, I think using probably Einstein's equations of general relativity, that the universe was expanding. So he also gets some credit here. Now, Hubble measured this expansion rate to be a much larger number, I think, than what we believe today. We have a much more precise measurement, but the measurement still holds up with data that we have today. And what I wanted to say before was how do we measure these motions? So you can think of the light that we take or we can measure from looking at galaxies in the sky. And light exists on something we call the electromagnetic spectrum. So the range of light that our eyes can see, we call this visible light, but that's only a tiny sort of chunk of the electromagnetic spectrum. And light that has higher energies, in the visible range at least, is towards like ultraviolet or bluer light. Light that is more red is lower energy, so it has longer wavelengths, and that's moving towards the infrared. But these other waves, like X-rays or gamma rays, which are very high energy, or microwaves and radio, which are lower energy waves, are also part of this spectrum. When we look at galaxies in the sky, they emit light that we can see and detect, and we can split up the wavelengths that we see this light in into different bins. So we can look at the light that the galaxy emits in visible, but also in maybe ultraviolet and infrared, etc. And when galaxies emit this light, if they're moving away from us, the wavelength of the light actually gets shifted. So this is called the Doppler effect. And you can see this point moving across here in this animation. So the point is emitting like waves. And as it moves forward, it continues to emit waves. But because it has a motion while it's also emitting the waves, the crests of the waves in the direction of motion get closer and closer together. The same thing happens with light, which behaves like a wave. So if a galaxy was moving towards us and it's emitting light waves, the wavelength of the wave kind of gets squished together. And we would call this a blue shift because the light is moving towards the bluer part of the spectrum where you have higher wavelengths or higher energy light. Likewise, if a galaxy is moving away from us, you get more spacing between these crests, and we call this a redshift because it's moving to the redder part of the spectrum. So the amount of redshifting we see or blue shifting that we see tells us how fast galaxies are moving. So this tells us something about this Hubble flow motion. But it also allows us to see the second part of this motion that I was talking about, which is their motion due to gravity. So the motion of galaxies due to their interactions, because they're very heavy objects that have a gravitational pull on each other, we call this in cosmology the peculiar motion of galaxies. So I said before that you can think of the motion due to expanding space as having like these coordinates on like a grid, and the grid is expanding. But you can imagine the peculiar motions of galaxies are the galaxies themselves moving through this grid instead. So yeah, they have these two components. One is due to a changing sort of like grid, and the other is due to them moving through the grid due to their gravitational interactions, which are sourced by how much matter there is in space around them and how strong gravity is. So this is my first poll question, if you want to launch it, Christian. Which I just thought it would be fun to put in here. How fast do you think the motions of galaxies might be able to get up to? So I'll wait maybe 30 seconds or so, I guess.
Yeah, we'll give it a minute.
Yeah, okay. Yeah.
It's so, people need a moment to think.
Yes, yes.
Okay, what do you think, Abby?
Wow, excellent. So yeah, the motions due to gravitational interactions of galaxies they typically have motions of up to thousands of kilometers per second. So it is quite fast. But you can also think of like the motion, which is due to expanding space. And that motion it's not really so simple to ask a question like this. So these peculiar motions can have a typical value because of like how much matter there is, how clustered it is, and how strong gravity is. But the motion due to expansion of space, it kind of depends on where you are relative to other things in the universe. And it's something that continuously increases with distance. And so it's actually possible even for galaxies very, very far away to be moving close to or faster than the speed of light. Okay, so moving on. So I wanted to talk about one thing that makes measuring peculiar motions very useful for cosmologists. And so I mentioned before something called dark matter. So this picture here I've borrowed from a collaboration that makes these amazing simulations. And they've got this wonderful plot here that shows from a simulation. They have this underlying dark matter field and this other, which is shown at the top in the blue. And then sort of in the other half of the image, you can see this normal matter field. So dark matter is something we don't understand very well, but we know is there. And I'll get to that in a sec, but more about that and how we know it's there. But the fact that we can look at not just at the positions of galaxies in space, which allows us to see the normal matter, which is visible matter, looking at the motions of galaxies. These motions, as I said, are driven by gravity, or the peculiar motions are driven by gravity and the amount of matter that's there. So even if there's matter that isn't visible to us, like dark matter, the peculiar motions of galaxies allow us to get a better view of how much matter is really there in between galaxies that we just can't see because it's too faint, or because it's dark matter, which is that it truly doesn't interact with light and we can't see it. So it gives us kind of like a much better view and more unbiased view of how matter is really distributed through space on different length scales. But what is this dark matter I'm talking about? So the discovery of dark matter is accredited to this scientist, Vera Rubin. So she found by looking at the motion, the individual rotations of galaxies. So galaxies themselves, especially like spirals galaxies, like the Milky Way, and makes like a spiral shape. These galaxies have a strong sort of rotation in a plane. But even galaxies that are not spirals, they have some sort of motion as well. And in principle, how fast they spin without flying apart should be dependent on how much matter they have going from the middle of the galaxy out to the edge. And you can sort of look at and plot by measuring this motion. In a similar way, you also use the redshifting of the light in the galaxy, but instead of from the whole galaxy, you're kind of splitting it up into different angles going out from the center of the galaxy to the edge. You can look at this velocity and go out to way to the edge. And in theory, if we have an idea of how gravity works, we should be able to make this plot and it should match up with a theoretical curve. But what Vera Rubin found is that that's actually not the case. And the only way you could sort of explain the results that she had is that perhaps there is much more matter there than we can really see. And what's really interesting is that this is like true for every galaxy. And you have this curve that instead of here, which should sort of drop off to very small numbers at very small distances, at much larger distances from the center, you see that it kind of has this flat curve, which is really weird. So it kind of implies that there's this, what we call like a dark matter halo, this kind of halo of dark matter that keeps going out from the edge that we can't see, but might explain why the curve stays flat. And even for galaxies that have very different profiles, so galaxies that you might see sort of like less light at the edge, which might imply, oh, there's less stuff there. You might expect it to drop off more than another galaxy that has more stuff at the edge, or we see more light coming from the edge. But what people have found is that it's kind of stays the same for every single galaxy. So it implies like that there really is like quite strong evidence for this kind of dark matter halo. And what we've also found, not just from looking at individual galaxies and looking at these, what we call rotation curves, you can look at clusters of galaxies, so big groups of hundreds or thousands of galaxies, and you can try and make an estimate of sort of how fast they should be moving and interacting with each other in a group based on the visible matter that we can see. And visible matter appears to be a significant underestimate of the total amount of matter that's there. So clusters of galaxies also support this idea of dark matter. And it's probably not that we're just counting the amount of normal matter that's there wrong. So this is what we call dark matter. And this was found initially in like the 1970s and confirmed later onwards, and has pretty much been a mystery to us since then. So this is my second poll question. So I said before, we've got normal matter. So normal matter being like stuff that we interact with every day on Earth. And in space, you can kind of just think of as all the stuff that makes up the stars and the gas. So all the sort of just gas that makes up galaxies. And then some component is the dark matter. And what fraction do you think might just be the dark matter?
Very interesting, Abby. Just very quickly, whilst people answer that, I've got a quick question there on
Yeah.
dark matter, because recently they actually found galaxies that have almost no dark matter or seem to have none whatsoever. And then there are others, smaller dwarf galaxies, that seem to experience a lot of dark matter. Doesn't that somehow make the thing far more complicated, the explanations?
Yes. So I think, yeah, I've heard that okay, maybe I've got this wrong. I actually thought it was the other way around, that the dwarf galaxies had much less dark matter, but I might be wrong. There's someone in my office that actually does exactly this topic, so I should probably ask him.
And I might have it wrong. Sorry if I have it.
Yeah,
I'm not sure.
yeah,
Okay.
I can't remember actually. But yeah, you do have these dwarf galaxies, and I think, yeah, it does make it kind of more complicated. So I guess I don't fully know the answer to that, and I'm not sure if anyone else does. Maybe they do. But I think that's kind of like a question of how galaxies kind of formed in the first place, and how the galaxies that are dwarfs, like tiny ones versus large ones, kind of formed. But yeah, I guess the truth is I'm not sure. Okay, well, the answer, most people got this right as well.
Good.
Excellent. So yes, around 85% of matter, we believe, is the dark matter. So a very significant fraction, which is a crazy thing to think, that we don't know what 85% of the matter in the universe is. And so aside from the fact that we think we need it for the galaxies to be spinning as fast as they do without flying apart, we also believe that having the dark matter there, because it doesn't interact with light, it means that when galaxies started like forming, so all the matter started sort of collapsing together to create the first galaxies, we think that having more of this dark matter that doesn't interact with light actually helped it kind of collapse faster, and that you might not even see galaxies today, based on how old we think the universe is, if you didn't have this dark matter here. Okay. So now I want to talk more about these galaxy motions, and this is more directly related to what I've been doing in my research. So this plot here on the left was made by some other scientists working on this in 2014, and it actually shows our local supercluster. So Laniakea is the name given to the big cluster of galaxies that we belong in. So I'm not sure, can you see my arrow moving on this plot, Christian? Yeah. So I
I
believe,
can. It's all good. Yes.
excellent. So I believe the Milky Way on this plot, my arrow's disappeared, is somewhere around here, sort of close to where this blue region is. So for context, what this plot is meant to be showing is kind of a reconstruction. So they've measured the motions, the peculiar motions, so the gravitational motions of galaxies in this region of space. And what they've done is they've kind of constructed what they call the peculiar velocity field. So it's a three-dimensional reconstruction of how galaxies are moving. So these lines on the plot are kind of like these flow lines into different structures. So there's a big structure over here called Shapley. We have Laniakea here, which is our supercluster, and this other one over here. So the white lines on our plot show the motions of galaxies that are kind of within, or the lines or flow lines, you can call them, that show where galaxies would be kind of moving sort of on average within our supercluster. And so I guess in this region, like this is kind of like gravitationally bound. And then you've got these other lines here showing the flows in other structures or away from voids, these which are the blue regions here. The green regions are where you have more matter. So this is an amazing reconstruction. And this kind of thing where you can look at how like you can use these motions to tell you where voids are, because galaxies will move away from the voids, and where these bigger overdensities are, because galaxies will move towards them, allows you to look at how big the clumping of matter is on these different scales. And we can use this to like measure how much matter there is in the local universe.
Abby, just a quick question for
Oh
understanding
yeah.
the scale here in giga-parsecs, or what's the scale of the diagram on the left? You have a
Yes. I actually forgot. I can probably check that at the end and come back
That's
to it.
okay. Just okay, don't worry.
Yeah, no, I should know that. But I would say I think it's probably safe to say it's gigaparsec scales. Yeah. So millions, I should say, of parsecs. So very large scales because this is a um, well, yeah, this is, or maybe megaparsecs might be more actually, because this is a cluster of galaxies, or a supercluster, as they like to call it. So hundreds or thousands of parsecs probably would be accurate. So yeah, this plot here was done in 2014 with a chunk of get data, or a compilation of the motions of galaxies. And this plot here shows a more updated version of kind of the same thing. So these authors in 2023 have done a very similar analysis, and they've reconstructed with basically the biggest catalog we have of peculiar velocities to date, these flow lines of galaxies and these different structures. So these different labels they have on the plot are kind of like different points of where the flow lines they found are sort of moving towards. And then down here in the red region is Laniakea. So that's our local supercluster. And you've got these other structures around it again. So what I wanted to talk about with this is, so you can look at this peculiar velocity field, we call it, and these flows of galaxies, and you can look at it in 3 dimensions and use it to test gravity. And one way we can kind of construct kind of like something we call, or we can construct an observable, we like to call it, called the bulk flow motions of galaxies. And we can compare the number for what this bulk flow is to what a model of cosmology predicts exactly. And comparing these two numbers gives us like a quantifiable way of saying like, oh, this motion or this amount of motion like kind of agrees with what we expect in a model. So what is this bulk flow? Well, the easiest way I think to explain with a bulk flow is with this diagram I've shown on the left, on the right, where I've added up or I've showed kind of like visualizing, you have these motions of individual galaxies, and you kind of add up all their directions together and get one big sort of direction, or vectors, we call them in math. And this summing of the motions of individual galaxies and kind of getting an average is what we call the bulk flow. And we can measure a bulk flow in like a volume of space and say, okay, like in this area of space or this volume, we have this measurement or this number for like the typical kind or the total motion of like the stuff in that chunk of space roughly. So yeah, that's what we call a bulk flow. And we can compare this to models. And by the way, this bulk flow, so we expect that if you had a very large patch of space, we expect, I guess, or you should expect that in a very large patch of space, if galaxies have on average like sort of motions in lots of different directions, you would expect them all the directions to kind of cancel each other out. So on very large scales, you basically should have a bulk flow that tends to be towards zero or a much smaller number. So I guess I'm not sure if that makes sense, but it comes from the idea that the universe is homogeneous. So it looks roughly the same wherever you are. And it looks the same in every direction. So it's isotropic, we call it. So you can imagine that if galaxies have like these, or there's these clumps of matter in different points in space that attract each other, and they're all like moving and being pulled in different directions, that they should all on average in a very large patch of space kind of sum to zero when you add their directions together. And on a smaller patch though, you would expect that not to be the case. So like if you're in a tiny little clump, you would maybe expect that clump is moving up to another clump kind of thing. So what models predict for these bulk flows? So this is this plot here is showing the magnitude of a bulk flow. So the kind of total motion or absolute value of that motion versus along this axis, you can think of the size of the little patch of space or the kind of scale or distance scale that corresponds to the size of a little patch of space. And like I was saying before, if you go out to very large distances or very large scales, we expect this bulk flow to get smaller and smaller and smaller. So yeah, this plot here is showing a theoretical curve. There's some other points on here, which I'm not going to talk about just yet, but I'll come back to that in a minute or so. So what I did in my research specifically for basically the first half of my PhD was kind of basically testing how well we can actually measure this bulk flow. So one thing that makes doing galaxy surveys really complicated is that it's not always just as simple as pointing a telescope in the sky, measuring some distances and saying, oh, like this is our measurement. We have to take into account that when we measure stuff in the sky, sometimes we can only see like a small fraction of what's really there. And we might not be able to look in all different directions. So this can cause what we call selection effects, and it can affect how well our methods of measuring things, such as a bulk flow, actually work. So without going into too much detail, what I did for a lot of my PhD was I made simulations of different sort of distributions of galaxies in the sky. So I kind of said like, okay, let's say I have a telescope and I measured galaxies like in this patch of the sky and maybe this patch over here, but I couldn't measure them in this patch over here. And maybe because of my telescope only being able to see galaxies that are so faint or so bright, I should say, I couldn't see things everywhere. So it kind of affects what I could see. And I recovered, what I did was I looked at measuring or what my methods of measuring the bulk flow would get by sort of applying it to the simulated data and then comparing that to what the real bulk flow in the simulation should be. So based on how I know the universe was kind of made in my simulation, what the real number should be. And by comparing these two things, we could sort of test how well these methods work. And so I spent a lot of my PhD just doing that a lot. And then we got to some real data. So this plot here is showing kind of like a projection of the entire sky for a bunch of data called CosmicFlows 4. So CosmicFlows 4 is the biggest compilation to date of data for the motions of galaxies or peculiar motions of galaxies. So this part here where you can't see much data sort of going through the middle, that's basically because when we look into the sky, the plane of the Milky Way kind of blocks our view of galaxies behind it. So we can't really see that stuff. In astronomy, you might hear it called the zone of avoidance. But that's another thing that affects our bulk flow measurements, right? We might want to understand how big the bulk flow is in a patch of the sky, but some of the data in a patch is missing because we can't see the stuff behind the Milky Way. So this is kind of like one of those effects that we have to take into account to make sure our measurement methods actually work well. And what I found in my result is, so my favorite plot actually is this one here on the left, where I've done two different measurements with two different methods. And the different methods work slightly differently because one of them is more sensitive to information on different sort of length scales. So it kind of places more weight on galaxies maybe further away than others, whereas the other one places more weight on the galaxies that are very close to us. So yeah, it makes it really complicated to sort of interpret how these methods work, but it's something we have to take into account because it's not always so simple to come up with a method that just accounts for everything in the way exactly we want with our data. But what I found is that basically these arrows here kind of show the direction or where, oh, sorry, go back one, where these bulk flows are going. So this point here with the star is something called Shapley, which I pointed out before in one of the previous plots. So it's like a known large density of matter. So you might expect it to sort of attract us and create a bulk flow in that direction. And this point here is a sort of hypothesized supercluster of galaxies that might exist. And in that region, people have called it the Great Attractor. So very inconveniently, this Great Attractor, which is sort of this idea, this mass that we think is there, but we can't really see because it's exactly in this zone of avoidance that I was talking about before. Well, the Milky Way blocks our view, seems to be pulling us there very strongly. And what's interesting and what hasn't just been noted by me and my collaborators, but by other people in the literature, is when you plot, so these points here show measurements of the bulk flow by various different authors in the literature. The red points are the measurements I made in my work. And what many people have noted, including myself, is that when you look at very large distance scales, this bulk flow, instead of dropping off to zero, like we expect theoretically, it tends to get bigger and bigger. So this right now is actually a bit of a problem. It's not a huge problem in cosmology, but it is something that people would maybe like to address, and we don't fully understand like why it's happening. Maybe our methods still aren't good enough. So we call that systematics when there's kind of issues with our methods that we need to address. But it might be that our model of cosmology just doesn't capture everything properly. But this is still something we have to do more research before we can sort of draw a very conclusive conclusion about that. Okay, so now I'm going to move on to part 2 of my talk, which is looking at using sound waves in the early universe to understanding neutrinos. And this comes to the particle physics side of things. So, okay, well, what are these sound waves I'm talking about? So in the early universe, I mentioned before that there was this rapid period of inflation. And right immediately after that, we believe the universe was like this hot, dense soup of different particles interacting. And because it was very hot and dense, basically sound waves could propagate through this fluid. And they have a fancy name that in cosmology, we call baryon acoustic oscillations, or for short, BAOs. But you don't have to remember that. Just think sound waves, early universe. So what this animation here is showing is how this sound wave could kind of, or the biggest sort of sound waves could move through space. And eventually these sound waves, when the universe got cooler, kind of stopped, and matter started collapsing in place, kind of where those sound waves froze in place and started forming the first galaxies we see today. So this is my third poll question. How fast do you think the sound waves moved in the early universe?
Okay, let's give them a minute. Just quickly,
Yeah.
I'll just throw in a question just to understand this correctly. If you look at the bulk flow, Because you
Yeah,
said the sum is zero, which is intuitively, as a scientist, I would say it makes complete sense to me. At the same time, we have the expanding universe, of course. So are you subtracting that or ignoring that? How does that work?
that's exactly right. So that's exactly right. So the bulk flow is not accounting. It's kind of, yeah, you're factoring out the expansion of space. Exactly. Yeah.
Thank you. Good.
So probably I've already given you a hint in this part here that C isn't the answer.
It is not. No. Yes. Okay, we'll see. Give it a
So I
few.
guess just to elaborate on that as well, like you might have heard that sound can't travel in space. Um,
Yes.
okay, so most people got this right. So it is in fact um, very high speed. Um, sound waves could move about roughly the half the speed of light in the early universe.
Mhm.
So yes, due to the very high pressure and density of this hot plasma of stuff, the sound waves could move fast. So the reason sound can't move in space today at all is because space is like quite empty on average. Of course, there's galaxies and things, but you go you go into like space just outside of our atmosphere, and there's like one particle per cubic meter or something tiny. It's basically a vacuum. So sound can't move through that because sound is vibrations of particles. Um, but a medium where there's lots of particles, there's nothing to stop the sound waves propagating. So we had these sound waves that I was talking about, and they could propagate through space. And this animation is giving you kind of like a one-dimensional view of that. But what you can imagine is that in 2 dimensions, these sound waves kind of formed like bubbles or rings. And these rings, or the size of these rings in cosmology, often gets called the BAO scale, um, or the sound horizon scale as well. So I said before, these sound waves propagated, and when they froze in place, because sound waves are vibrations of particles where you have like over densities kind of vibrating. When they froze, those kind of vibrations sort of froze in place and matter started collapsing. And the fact that that happened actually left an imprint of how fast these sound waves could travel in the early universe. And how fast those sound waves moved did depend on how fast the universe was expanding and how much time those sound waves had to be able to move in the age of the universe at that point. So it allows us to understand somewhat, but from measuring the scale, how uh, how much stuff is in the universe because it impacted this. So this evidence of the BAOs and the fact that they exist was actually first discovered in yes, I think 2005 and 2007. So roughly, I think these should both say 2005 actually. Yes, I think that's a mistake. That should say 2005, but roughly at the same time, these two groups measured this BAO scale in the data. So this plot is surprisingly blurry, but without going into too much detail about what this is showing, basically, when you look at the clustering of galaxies in space, you look at how like much they're clustered together and look at that on different length scales. You should expect theoretically to see this bump that you see here that corresponds to the BAO scale. So you can think of it as like an excess probability of seeing galaxies separated by this length scale due to how these sound waves moved. So it was first measured in 2005, but now, so I mentioned before the DESI collaboration, the Dark Energy Spectroscopic Instrument Collaboration. They published their first year results on the BAOs earlier this year. And it's basically the most precise measurement we have to date. So you're still seeing this bump in the data like almost 20 years later. So this plot here is showing the bump for like one group of galaxies. So probably don't need to read all this text. But LRGs are just a type of galaxies measured in the DESI data called luminous red galaxies. But they had a bunch of different traces and had a bunch of different sort of, you can think of it as different distance scales. And these plots on the right are just showing the bump measured individually in like different kinds of galaxies, which is super cool. And because this, oh, yes, I forgot about this. So my supervisor is Howlett on this paper here. Some astronomers last year actually found, looking at some of this data, so I mentioned before, CosmicFlows 4, the data that we use for the peculiar velocities. In that data, they actually found this kind of ring that happens to have a scale that corresponds to the BAO scale. So they suspect and showed with some statistical significance that this bubble they see in this data could potentially be a single kind of BAO ring, which is really cool to see. But what I was saying was that this BAO scale, because it in principle should be like the same sort of size wherever you are in the universe, it's kind of like a giant ruler. So you can imagine if I have a ruler and I move it backwards, it's going to get smaller and smaller. So if I look at this BAO scale at further and further distances, it's kind of like a standard length scale in the universe. And it allows you to measure kind of like what distance scale you're looking at very, very precisely. So this plot here is showing the bumps that I was just showing before for different kinds of galaxies. So this here, if these bumps or these data points for each of these bumps lied exactly on this flat line, you would have what we expect for what we understand is like our best model of cosmology. This dashed line was the model they found to be the best fit in their data. Talking about that is a whole different other story, so I won't go into that. But basically, you can imagine that these bumps here, these individual points that represent each of these bumps from different kinds of galaxies, are showing distance scales going way back at different distances in the universe and thus different times in the past because it takes so long for the light to get to us. But the main thing I want you to get out of that is that we can measure this sound horizon scale with this bump. What does that have to do with neutrinos? And firstly, what are neutrinos? So I realize I'm going a little bit over time. Is that okay, Christian? Okay.
So it's very interesting. Go on. It's all yours.
Okay. Awesome. Yeah, what are neutrinos? Well, we have this standard model of particle physics. And you might have heard, like from high school physics, there's protons and neutrons and electrons. But what we found over the last 100 years or so is that protons and neutrons and electrons, so electrons are what we believe to be a fundamental particle, but neutrons and protons are not fundamental particles. So they're made up of these other particles called quarks. And then we've got these group of particles we call leptons that includes electrons, but these other kinds of particles called muons and taus, and three kinds of neutrinos. So you have an electron neutrino. It's called that because it's associated with sort of reactions where you have an electron. And likewise, muon and tau neutrinos are associated with reactions where you have these other two kinds of particles. So neutrinos are kind of like a really hard to understand particle. So like we do lots of experiments where we can kind of measure the masses of different particles and measure their properties. And we have this standard model of particle physics, and a lot of particles kind of match up pretty well with what the standard model predicts. But neutrinos kind of don't. So neutrinos are very, very strange. They are a weakly interacting particle. So what I mean by that is that they have a really low chance in general of interacting with another particle. So in particle physics, they like to call this a low interaction cross-section. So it makes them hard to detect in an experiment, but they're also very, very light. So the standard model actually says that neutrinos should be massless particles. And people basically believed that up until 1998. And then some terrestrial experiments showed that that basically couldn't be true. So now neutrinos are kind of like this weird, mysterious thing because we don't understand why they should have mass. And even though we know from experiments that they have mass, we actually haven't yet, with a terrestrial experiment, been able to say how massive they are. So, yeah. And the reason why they're interesting to cosmology, and this is my favorite thing, or my most interesting thing that I've been able to study in my PhD, is that they have their presence in the early universe. The fact that they exist has a really strong effect on how large-scale structure formed. So just to explain that, So I said it before, in the early universe, you had this like hot soup of particles right after this rapid period of inflation that we believe occurred. And then what happened was all these particles kept interacting, but neutrinos, I said, have a very low chance of interacting with other particles. And because the universe was expanding and crazy stuff was happening, it kind of made it hard for them to keep interacting with the other particles. So we have this thing, this event that we call freeze out, or basically just when the neutrinos just stopped interacting with the other particles. And basically what this means is that because they didn't interact, they could free stream or basically just move through space without having more interactions. And because they did this in the early universe, whereas other particles didn't really do this, but they have gravity, they had a really interesting effect on how matter formed. So this next slide is showing basically a simulation. And in this simulation, you can see over here, we've got like how the universe is formed with lots of structure. And then if you go towards the other side of the plot, you have the bigger structures, but the smaller ones kind of get washed out. And basically what theory predicts is that because these neutrinos free streamed in the early universe, depending on how massive they are, it kind of tended to wash out the structure on different scales. So if they were very massive, you would see something more like this. Because we don't see that, we kind of know that neutrinos aren't really massive particles from cosmology. But what we can do is we can look at this structure in the universe and use it to sort of say, well, neutrinos must have a mass smaller than this. And the idea with cosmology and with the DESI survey as well is that maybe we could eventually, with enough data, say the neutrinos have a mass that's exactly equal to a certain number. And this would allow us to help the particle physicists. The only problem is that it's harder to convince them that our measurements are good, because there does tend to be a lot of dependence on our models to get this right. And there's still probably a lot of work to do on that. But another thing that you can look at is how the neutrinos impact the sound waves. So this is coming back to what I was talking about before. You can measure this peak in the data that tells you about the sound waves in the early universe. And we like to do this special analysis where so if you're an engineer, you might have heard of this, but we like to do this sort of mathematical transform to the data. It's kind of an equivalent representation of the data, but looking at it in a way that makes it easier for us to pick out certain features. When we do this Fourier transform, this BAO peak that we see, or this sound horizon peak, looks like a bunch of wiggles. So in cosmology, sometimes we call them the wiggles. And what we know is that if there is a different number of neutrinos in the universe, these wiggles actually get shifted, or they get what we call a phase shift. So what this is meant to be measuring here, or showing here, I should say, is if you change this parameter over here, that's this number moving, that represents how many different kinds of neutrinos there are in the universe, it shifts these wiggles back and forward. So we can measure these wiggles and try and measure this shifting to tell us something about the number of kinds of neutrinos. So you might be thinking, I just said, oh, there's 3 kinds of neutrinos, so why do you need to measure this? Well, we think there's 3 kinds of neutrinos, but in principle, there could be something that behaves very similarly to neutrinos in the early universe, or there could maybe even be another kind of neutrino that is just not predicted by the standard model. So by using these wiggles in this special analysis, we can pick out this shifting of the wiggles that would come from changing the number of kinds of neutrinos. And basically we can say, well, the cosmology data says there's this many kinds of neutrinos. So yeah, I think that's basically everything I wanted to say. Sorry for going a little bit over time. And I've just put here a couple of links to, Christian found me through Astrobytes. So this is just some stuff I've written for them if you want to see. And I've written some other blog posts talking about my research on these other links here, or the papers if you're interested. Yeah, thank you.
Thank you so much, Abby. Really fantastic, so interesting. If you just don't mind, just stop sharing your screen and we can see you better. And then I'll just ask you one question. I mean, the last part is really fascinating and it's absolutely mind-boggling when you talk about neutrinos. Suddenly, you go to the other scale, and I find this very interesting that these evasive neutrino particles will. I mean, as you correctly said, when I studied physics, we thought they were massless. Now they have a small mass or whatever it is. We don't even know. We don't even seem to know how many neutrinos there were, at the time of the Big Bang. So there are lots of open questions there. So a very simple question, really, at least for me to understand. Why is it then that neutrinos are so significant here? Couldn't it have been something else that causes the washing out of the small structures, or can it really only be neutrinos?
So, yes, I guess in theory it could. So, in our models for dark matter, we say that dark matter is probably cold dark matter.
Hmm.
So it sounds weird. What does it mean to call it cold? Well, for particle physicists, cold dark matter means it's like probably a heavy particle that doesn't have a lot of speed. So in principle, you could have something called warm dark matter. But I think lots of models have kind of ruled that out, and most people don't think dark matter is made of warm dark matter. But you're right that it could also be something else. So I guess the idea of measuring this number of neutrino species that I was talking about on the last slide, or this, we actually have a special name for a parameter called the effective number of neutrino species, because that parameter would also capture the effects of another particle that would have the same effect or have a very similar behavior. But we don't know for sure if it would be a neutrino. So we expect, right, that we expect theoretically that this number should be very close to 3. But if we measure 4, then, that's telling us that maybe there's something else that's creating this washing out. And that's what makes it so interesting.
Yes, it does. Thank you very much. I'll go over to the audience questions now. So, Max, the author of The Visible Universe. Hi, Max. Very nice to see you. Going back to the first DAISY chart, that was right in the beginning. I remember that. What does the y-axis represent, and what is the
Oh,
diagonal
yeah.
y due to that? Yes. Okay.
Yeah, sorry. So I probably should have made that more clear. I think both axes are distance. It's just like a 2D projection of some of the data. Um, I guess it's probably just on a diagonal because maybe it looks nice plotting it that way. But it might just also be that like you have sort of like a cone in the sky with the data that they're showing because we don't have like a full like the DESI has like a certain what we call footprint in the sky, like it only looks at a certain patch. So if you plot it in 2D, it's going to look sort of like a little cone.
Good, thank you. And Richard is asking, wait a second, let me just get this correct here. Regarding light speed, I almost know nothing about Cherenkov radiation. Reactor blue glow water speeds faster than the speed of light. And then he goes on, question, do your studies consider speed of light as a constant?
Um, yes. So I said before, maybe you heard that okay. So obviously the speed of light, yeah, it depends on the medium. It's might or yes, light will move in a different speed in a different medium, right? Very slightly. But I guess in space it's probably
Mhm.
um it should be on average roughly the same speed through most of what would be largely empty space. Um, I guess if you were considering a really dense medium, though, maybe you would have to take that into account. But I also mentioned before that galaxies can move due to the expansion of space faster than the speed of light. And that might sound really weird because nothing is supposed to move faster than the speed of light. But actually, you can have, due to expanding space, you can sort of think that the galaxies themselves aren't moving through space faster than the speed of light because they're not like moving through like this grid of coordinates I was talking about before. But because the grid of coordinates is moving so fast, you can see what appears to be faster than light travel of galaxies.
Excellent. I'll skip the first question from Dennis because he rewords it here. Just one second. Um, do individual galaxies in a cluster rotate about the gravitational center?
Yes, I think that's true. So I think if you have like a cluster of galaxies, I think so. This is not something I have so much expertise on, but I believe there are often like galaxies that sit right in the middle, and then that are the heaviest ones, and then you have other ones kind of orbiting around them. And the fact that that does happen actually complicates bulk flow measurements a little bit as well.
Very good. And this was something I was also wondering about. Didn't Zwicky find dark matter much earlier? That was about Vera Rubin. Of course, she is rightly credited for her excellent work, but that's I think, just a question there, right?
Oh, right. I'm not actually sure. I would have to look into that. Yeah.
Okay, fine. Natalia, nice to see you here. Thanks for this interesting talk. I completely agree. What do you think about the Hubble tension? How could you explain it?
Okay. Well, if only I knew the answer.
It's a difficult
If
one.
only.
It's very difficult.
Yeah. So I guess for the audience, the Hubble tension is this idea that if you measure this expansion rate, this that I mentioned before, you had this plot, we had distance versus velocity versus distance, and you had this slope. The angle of that slope basically tells you something called the Hubble constant, which you can think of as the expansion rate, and people quote this Hubble constant. And there's this problem, a big problem in cosmology, where a bunch of probes measure a number that's about 67 kilometers per second per megaparsec. And a bunch of other probes, particularly these other probes, tend to be more focused on data that comes from what we call the late universe, or like would be stuff that kind of formed or light that has traveled to us in the later universe versus stuff in the earlier universe. These later universe things get a larger number, around 73. And even though the distance between 67 and 73 is very small, like they seem close together, these numbers just seem to be really consistently different. And no one really knows how to explain that yet. So there's probably hundreds, maybe even, I'm not even sure, maybe thousands of papers on the Hubble tension, probably hundreds. But yeah, it's a big topic in cosmology. And if I knew the answer, I might get a Nobel Prize.
Yes, you would,
So I
for
think it's fair
sure.
for me to say I actually have no idea. I'm very sorry.
Thanks for that. And John is asking, how do galactic collisions, what effect do they have on the bulk flow, like M31 and the Milky Way? Yeah, that's what he's asking.
So I think like galactic collision. So I think the Milky Way is not meant to collide with our galaxy. Sorry, the Milky Way is not meant to our galaxy is not meant to collide with Andromeda for quite a while. So I would not expect it would have much of a effect, because when we're measuring a bulk flow, we're kind of picking a point in time roughly and just measuring the motions at that moment. And because these collisions happen over maybe millions or maybe even billions of years, I'm not sure, because they happen on very long time scales, I imagine it wouldn't have too much of an effect. I mean, I guess you could be measuring the bulk flow and seeing two galaxies collide in that moment, but yeah, I mean, we expect, because of the bulk flow is meant to be capturing these gravitational interactions, like it would still give us the right answer, if that makes sense. Yeah.
Yes, thank you. And Peter, nice to see you here. Interesting one. In the beginning of your presentation, you showed a slide with the curves of radiation, matter, and dark matter. Does this mean that there's always a balance of equilibrium of all the matter that exists?
So if I understand what you're asking properly, so I think you're saying, do I always think that like there has to be a balance between like the force that's making the galaxy spin and the gravitational force like that's holding it together, so as well as like the acceleration that it has rotating. And yes, I mean, I guess it's a fundamental principle in physics that um, uh, these forces kind of have to balance. There has to be like this equivalence to sort of satisfy conservation laws, like conservation of energy. So yes, I would say that's true, I think, if I answered that, if that's what you were asking.
Yeah, I
Yeah.
think it's conservation of energy momentum and so on. That's my understanding, which also then relates to energy, matter, and everything else, right? I think that's what he means. Is there a balance of everything, right? That's
Yeah.
that would be the
Yes.
assumption. Yeah. Okay, good. Next one. Are superclusters, this is, I think you've answered that already, in a way. Are superclusters gravitationally bound?
I think, yeah, I think if you call something a supercluster, it's because you think it's bound. So on some like time scale, clusters of galaxies became bound and they're all orbiting around each other. So, yeah, I think yes is probably the right answer to that. Yeah.
Good. And oh gosh, sorry if I can't pronounce your name correctly. Agnes. Yeah. Sorry about this. See, I wanted to ask about the bumps. Can you explain the chart?
Yes. Sorry, I guess I skirted over that a bit because I was trying to avoid going into statistics too much. But so what is the chart showing? So I mentioned before that these sound waves, they propagate and they're like an overdensity of matter moving. If this overdensity froze in place, then you have like a overdensity of matter that's kind of you find on a typical length scale in the universe.
Mhm.
And what happened was matter started forming. So what you found, or what you would find is that galaxies started forming on these different scales, but more galaxies would form on this scale that corresponds to this length scale. And now what is the chart showing and why is this a bump? The chart is kind of showing, if you look at different length scales, what is the probability of finding galaxies separated by a particular length scale? So at different scales, like do I find many galaxies separated by maybe 50 parsecs, or do I find many separated by this many parsecs? And you're kind of plotting this probability. And you expect that a peak is telling you that there's lots of galaxies at that scale, that there's lots of clustering on that scale or separated by that scale. And because we see this bump, it's kind of telling us that is where we see this excess clustering, and it corresponds to the length that we believed sound waves moved and then started collapsing. So that distance scale, that separation scale, is the distance sound waves traveled in the early universe. It's kind of a lot to absorb. Like there's a lot of math in that kind of, but hopefully that made sense.
It does. Thank you. And Yanari is asking, does the gravity of superclusters affect the motion of galaxies in general?
Yes, definitely. So when we're measuring this bulk flow, like that is exactly what we want to capture, this gravitational effect on these clusters of galaxies. Yeah.
Excellent. Then the final question from Michael, and then we'll let you go back. Oh, one more, but then we have to really stop. You have to give Abby the chance to rest after this because she's got up so early. So really. Okay, so that'll be the final questions. Assuming dark matter is mainly responsible for the large structural universe and that neutrinos have low cross-section of interaction with baryonic matter, then how do neutrinos change the large structure because they presumably have even small cross-sections to interaction with dark matter?
Okay, yeah, that's a really good question. And there's a lot of parts to that. So in principle, I mean, even though we don't know completely, like in theory, dark matter doesn't interact with anything. Um, but well, except for gravitationally. So it doesn't have interactions that are like through electromagnetism or any other kind of force, like the weak or strong nuclear force. In theory, it's just gravitational interactions. So um, I guess what I was saying was I should have been more clear actually now that I think about it. I said that neutrinos have a low interaction cross section, but I guess this is talking about not gravitational interactions. Like they have mass, so they will interact gravitationally. And their mass and gravity is kind of part of what affects this washing out of structure on different scales. Because as they move, because they have mass and because there's like an equivalent between mass and energy, they're kind of pulling away energy and that's sort of, or they're carrying energy. And that's kind of what is washing out this structure on different scales. So hopefully that answers the question.
Yeah, very good. And then a final question from Julian. If the great attractor exists, how big is it?
Yes. Okay. I actually don't know. Um, if it, yeah, I think that's
That's
the only thing I can
fine.
say. I don't know. But it would be a significant, like, it would be like a supercluster of galaxies for sure. I think because it has a significant gravitational effect if it's pulling lots of things in that direction. Yeah.
Well, thank you, Abby. Once again, I think you handled that superbly. My really greatest compliments. That was it's such a difficult subject. And for your very young age, it's amazing how you can comprehend this because you've really chosen a very difficult subject. So really fantastic. Keep up your work. very interested. If you ever want to come back, you're very welcome, because it's just such a big topic. Or if you have others from University of Queensland who want to talk, we'd be delighted. As you can see, the audience is very interested, very engaged. So anyway, thanks to everybody else asking, engaging, making this possible. We want to definitely keep up the webinars here. So if you know anybody who wants to talk, please let me know. So thanks on Abbe, on behalf of everyone. Thanks for getting up so early. Have a good time in Brisbane, get some rest, and then hopefully you have a great weekend. Thank you, everyone, and goodbye.
Awesome. Thank you so much, Christian.